I would like to introduce our next presenter, and that's Paul Higgins, and he is a research fellow in solar physics at Trinity College Dublin. He does know our dear Claire, and he is currently a visiting researcher at Lockheed Martin Solar and Astrophysics Lab. His main research interests are in sunspot evolution and eruptions, as well as solar eruption prediction. Paul is a member of the Max Millennium Flare Forecasting Team. I want to say that again. Max Millennium Flare Forecasting Team. He is also lead scientist on the Sunspotter Zooniverse project, and he's directing the student-to-student science or student-to-scientist program funded by the CS4HS grant to make science learning in Ireland more interactive. Can you tell us a little bit more about that, Paul? But please, Paul, take the stage. Welcome.
Okay. You want to know more about the Google project?
Is that what that is? I just said it was the CS4HS grants, and I don't know. I don't know what that is. Maybe somebody else does, but I don't.
Yeah, so it's one of the Google Foundation grants that they give out for science education and outreach, and this particular one is to get computer science into classrooms, basically. So we wanted to do a variation of just simple, computer science coding workshops. So we're combining CS with science, and we're using Scratch to make physics simulations, and we're doing teacher development workshops and student workshops in Dublin. So right now we're just about to run our first teacher workshop. At the end of the year, we'll be applying for more funding for next year to keep that going, and I'm also in the process of applying for funding here to start up an American version of the project. So you can check it. I'll post the website here. Student. There you go. Did you have any more other questions, or should I just get into the talk? Cool.
The stage is all yours, Paul. Absolutely. I wasn't quite sure what that was, so thank you for explaining it to us. But yes, it's all yours.
All right. Full screen. Can you guys see the full screen page? Okay, it looks okay.
Yep.
All right, let me get the chat window out of the way. Okay. Yeah. So as Andy mentioned, I'm studying sunspots and how they evolve and what causes them to erupt. So Sunspotter is basically a citizen science project. It's just a research project for the research I'm working on, where we're trying to measure sunspot complexity, and I'll explain why that's important, why that's interesting, and why we want to do that. So the goal of this talk is really, I'm trying to inspire you guys, which I assume most of you are teachers at some level, inspire ideas or ways that Sunspotter can be used in your classrooms and maybe integrated into your curricula. So in this talk, I'll give a summary first of the science of Sunspotter. And I wasn't quite sure what level people were at with, physics and whatnot. So I have some simplified slides and then some more technical slides to get both sides of people have a bit more knowledge about sunspots.
Oh, we have something, but everybody will be interested in all of that, Paul.
Great. So I'll talk about how the interface and how the project works behind the scenes. I'll talk about some results that we got from the last round of Sunspotters that finished up in March. And then I will talk about some of the activities that we've run with regards to education outreach, and show you some of the materials that are available right now. There's not a huge amount. And then talk about some future materials that might be useful for you guys. So what I'm really trying to figure out is, what materials could we develop with you or with whoever that would actually be useful and that you guys would actually be interested in using in your classrooms. So first of all, just to give a very basic idea of what are sunspots. So if you look through a solar telescope that has a filter on the front, blocks out most light, you'd probably see an image similar to the top left corner. Let me see. Annotate. There we go. Spotlight. I assume you can see like a little laser beam type thing. So this is sort of a sunspot in visible light. And then we can actually take an image of the magnetic field distribution on the surface of the sun, so we can see where magnetic fields are coming out of sunspots, which are the black areas, and where magnetic fields are going into sunspots. Sorry, into sunspots is the black areas, and out of the sunspots is the white areas. So you can see this is a pretty complicated sunspot where there's really a mix of magnetic fields going in and out. If we take an image of the atmosphere of the sun, you can see that the magnetic fields permeate into the solar atmosphere, and the hot ionized plasma in the solar atmosphere gets tied to the magnetic field lines in three-dimensional space. So we can take the extreme ultraviolet image, which is this one, and it's really a map of the 3D magnetic field of above sunspots in the solar atmosphere. So to demonstrate this, which I did to a bunch of students last Friday when we relaunched Sunspotter, I got a bottle of baby oil, put some iron filings in it, and used a magnet, and I was able to show sort of generally what the magnetic field looks like for a single sunspot, where it's just magnetic field coming out and it looks sort of basically like a circle. Or if you put the magnetic field, if you put the magnet against, like lay it flat against the bottle, you see sort of a dipolar, we call it a dipolar structure, where you see two sunspots and sort of loops connecting in between. So they seem to have fun with that, and maybe give them a bit of a more physical picture of what sunspot magnetic fields look like. Let's see. So, sorry, one sec. Scientifically, what we really want to do is obtain a quantitative measure of complexity for sunspot group magnetic fields. So we're trying to answer two different things scientifically. One is, do more complex sunspot groups produce more eruptions like solar flares and coronal mass ejections? Also, can an accurate knowledge of complexity, sunspot group complexity, improve the forecast that we give for eruptions? So as Andy mentioned, I'm a forecaster, a space weather forecaster, and we really go on intuition a lot, but we want a more numerical, automated method of forecasting. And at the moment, most methods are pretty unreliable. So hopefully better quantitative knowledge of complexity could improve these forecasts. Lastly, we want to figure out if sunspot groups are born complex, or do they evolve to become complex? And this is a part of the project that's just been launched last Friday. So the first part that I talked about, phase one, we've completed the data, if you want to call it the data acquisition phase, or people have basically gone on the website and ranked all the sunspot groups. And I'll talk about how they actually did that. Okay. As a space weather forecaster, if you want to call me that, basically we look at data, look at real-time data, we'll look at what sunspot groups look like right now on the sun when we make our forecast. And we look for certain patterns that tell us semi-intuitively whether the sunspot group will erupt or not. So here you can see on March 28th, I saw this interesting looking sunspot group that looked like this. And then on the next day, let me get my spotlight. This is what it looked like the first day, and on the next day it looked like this. So you could see there's some stretching going out on along the top of the sunspot group. And then when you look at the magnetic fields, it looks like the line separating the white and black areas got a lot stronger and more stretched out. And then if this movie was working, which it's not, you would see an eruption happened actually the next day. So we successfully predicted that based on the patterns that we see visually. And of course, one of the patterns we look for is how complex the sunspot groups are. So as simple as I can put it, what we know in solar physics is that small, simple sunspot groups produce small eruptions, and much bigger and more complex sunspot groups produce much bigger eruptions. So if we get a bit more technical, there are a bunch of different ways of actually, I guess, quantifying complexity, but it's not really true complexity. It's sort of a numerical method that someone's developed to get, an estimation of complexity. But it turns out these proxies for complexity don't do that well and are really hard to physically interpret. So the most, I guess, proxy for complexity that's done the best so far is this thing called the expert classification, which is it's called a Hale classification in this case, where people classify sunspot groups using a couple of different schemes. So an alpha sunspot group is one that's just a single sunspot, so either just white or just black magnetic fields. A beta has both white and black, and then there's, you can see in this list here, there's gamma, delta, beta, gamma, delta, and those are just more complex, mixed up classifications. So there's a group of Air Force guys that are trained, and they go on every day, look at what's on the sun, and they basically put out a list of classifications of the sunspot groups that are there. And people have done analysis on all these sunspot group classifications that these Air Force guys have done. And you can see that from this plot here, more complex stuff, which are these red dots here, produce much bigger eruptions, which is this line on the y-axis. Also, much larger sunspot groups produce bigger eruptions, whereas the more simple ones, the alphas and the betas, produce much smaller eruptions. So that's sort of like this is sort of the main work that people base all of their complexity stuff on. And we're trying to take this further and actually make a more continuous measure of complexity rather than just having a few classes of complexity. So I was trying to explain, yeah.
This is Nancy. I'm going to interrupt you just for a moment. We've got a couple of questions on the chat, and I'm wondering if you'd like to take questions as you go along or wait for the end.
Absolutely, yeah. No, sorry, I should have mentioned that. Please interrupt me at any time. I was trying to make this more conversational. Let me see what we have here.
So I think a little ways back, Vic had asked what frequency is used to see the magnetic fields.
Oh, okay, right. That's a really good question. So these magnetic field images are actually, we actually need to take something called filtergrams, which is an image at a very specific frequency. And we take about, I think in this case, there's 5 different filtergrams that are used to make a single magnetic field image. And each filtergram is at a different place along a spectral line, which is very affected by the magnetic field. So with stronger magnetic fields, this spectral line moves around due to the Zeeman effect. So we take images at different points along the spectral line, and then we use something called an inversion method to get from spectral line images to a magnetic field image. I hope that answers that question. So these are, yeah, so the images that I've showed so far are with HMI, but for phase 1, we've actually used images from the magnetic, what's it called? The Michelson Doppler imager, which is from SOHO and actually has a much poorer resolution than HMI, and the images aren't as pretty. But we will be switching to HMI probably in a number of months for the 3rd phase of the project. Any other questions?
There was a question about HMI, what it stands for, which I believe is helioseismic and magnetic imager. But I'm wondering if you wanted to say anything more about that. Yeah,
so HMI and MDI, so HMI is this newer instrument that's on the Solar Dynamics Observatory, SDO. And it has a really good resolution spatially and temporally, meaning like you get a lot of images per minute with really high spatial resolutions. You can see really detailed magnetic field structures on the sun. MDI has a sort of a 96-minute cadence, and the spatial resolution is about 4 times worse. But overall, the instruments are pretty much the same in that they use these filtergrams to take pictures along a spectral line and then go from that to magnetic fields. So they work pretty much the same. HMI is on the Solar Dynamics Observatory, and MDI, which is the one we use for phase 1 of this project, is on the SOHO spacecraft. So I gave part of this talk to a group of sort of 6-year-olds to 12-year-olds, and this is one of the images that I have shown here, where I was trying to explain what complexity actually means. And simplest definition I could find was having a lot of different parts in a really intricate arrangement. And something that I thought they might have some context for was comparing an old-fashioned phone to a smartphone. Let's see. Does it image the plasma in the field, or can it determine the field itself? Can you explain that question a bit more, Vic?
I'm still way back at the beginning, trying to determine how you can get a photograph of a magnetic field. And that still doesn't sink in. And so I'm trying to figure out, well, if you're actually detecting the plasma in the field, or can you detect the field itself?
Right. Okay. So here, what I've drawn, hopefully you can see that image I'm drawing right here.
Yes, I can see it.
Yeah, so this is a spectrum, right? Lambda means the wavelength of the light, and the I is the intensity of the light. So if we had a spectrograph, we could see, a spectral line, and if we aimed the spectrograph at the sun, we might see different spectral lines on the sun. And if we zoomed in on one particular spectral line, we would see that. Now, we can tune our imager to just take an image at one particular frequency. Let's say this one here. So we get an image, and basically the intensity of the image is just given by the intensity that you get from that part of the spectral line where I've drawn that line right there. So we'll get an image. Sorry,
so the brightness of that frequency.
Yeah, exactly. The brightness at that particular frequency. So we get an image of the sun. Let's pretend that's the sun because it's hard to draw with my finger pad. At one wavelength, and then we get another one at another wavelength. Let's draw two there. And that might be, let's say, in the core of the line right here. And then a third one over here, let's say. And then we basically combine all of these images by subtracting subtracting the images from the different parts of the spectral line. And there's a particular equation that gives you what the magnetic field is based on the difference between the intensities of those different parts of the spectral line. So the Zeeman effect basically causes this spectral line to move this way or this way. If the magnetic field is pretty weak, the spectral line moves a little bit. If the spectral line is, if the magnetic field is really strong, you actually get a splitting of the line that looks something like that. So you'll get actually a line core there and a line core there. And the difference in spectral distance between those two line cores of the split spectral line is directly related to the magnetic field. So does that help a bit?
Yeah, and does it give you, then where do you get the direction, whether it's coming in or going out?
Oh, right. So whether it's coming in or going out, basically I'll call it delta 1 and delta 2. Let's say the subtraction of those give you the magnetic field. Whether that number is positive or negative will tell you which direction the magnetic field is going. And this is just to measure the magnetic field in the line of sight, whether it's coming out or going in. That was a really simplistic and sort of misleading answer because we actually take filtergrams along the spectral line like this, but we also polarize. We take filtergrams with polarized light. So we use a polarizer to just take, right circularly polarized right circularly polarized light and left circularly polarized light. So it's actually a bit more complicated than that, but that's sort of as simple as I could explain it without some more plots, I think.
That's a start. Thank you.
Okay, no problem. Let's see, how do I erase this now? Okay, let's go on to the next slide then. Yeah, please stop me at any point if anyone's feeling lost. So this slide, I was basically trying to show that there's a range of complexity of sunspot groups. the most simple ones either just have white or just have black, or have maybe white and black, and you can draw a pretty, you can sort of draw a line right down the middle. And that's a pretty simple configuration of sunspot group magnetic fields. As you start to mix around the white and the black, you get something more like the middle image. However, if you keep mixing around the magnetic fields until you just have noise or speckles of white and black everywhere, you get sort of the third one, and it becomes simple again. So what I was trying to get at is there's this sweet spot of where the complexity lies between just a simple configuration and noise. And that's what we're trying to determine with Sunspotter. And computers have a really hard time of doing that, but people can pretty easily say that the middle image is the most complex. So I tried to do an analogy with Legos, where if you have all the Legos of different colors separated into little places, it's pretty simple. Or if you just have a big mess, it's sort of simple to just say it's a mess. But in the middle, you can build some pretty interesting structures with the Legos, and that's sort of the complex thing that we're trying to get at.
Okay, I'm going to ask another question right now.
Go for it.
On your website, you have this setup where you can choose complex and simple.
Yeah.
Okay, so that I understood, but is there a place that you can check yourself on, are you identifying these appropriately?
Oh,
kind of a self-check, so that you know, kind of self-train that, okay, this is what simple looks like, this is what complex is. And you can go through it, and then is there some way to check it and say, yeah, you got most of them right, or boy, you don't have a clue?
That's an interesting point, yeah, and that's not something that's really built into the website. What we did do was we have sort of, not really a tutorial, but sort of like an explanation of what we mean by complexity. And there's a link at the top of the website. If you click, I think it's science, maybe. Or I think it just comes up as what do we mean by complex if you click on that on sunspotters.org. And that gives you some examples of what, you know, what's comparing two different images, and then we tell you which one we think is more complex. So it sort of gives you an idea of what we mean. But in the end, no, we can't really do that because we don't really, I mean, this data set has not been classified in terms of complexity, so we don't really have anything to match it against. Once you've classified an image, you can then click on that image and look at some metadata associated with it. So you could see, you know, did the Air Force classify that image as an alpha or a beta gamma delta? So if you're classifying a bunch of alphas as more complex than a bunch of beta gamma deltas, then you're probably doing it wrong.
Okay, I missed the piece on how to check it. So if there's a check, okay, I'm happy.
Okay, yeah. Yeah, so this is just an example that I showed to a bunch of kids, and they all unanimously pointed to the B as being the more complex one. And I've done this test to groups of scientists, groups of general public, and everybody seems to have a real intuition for which one is more complex. So I've trusted the crowd overall. In this case, there's a movie that would have played if I'd compiled my thing correctly, that you would see an eruption actually happen in B, whereas nothing really happens much in A. So that shows that complex sunspots often have a lot more going on in the atmosphere above the sun. This is an image in 304 angstroms, which is extreme ultraviolet. So you're seeing just above the atmosphere, just above the sunspot in the solar atmosphere. So
I'm going to interrupt one more time. Is this the technique then? For example, if you go to spaceweather.com, they start giving you percentages of chances of various types of eruptions. Is this the concept that they're using? Are they taking your data or what on how they can predict, well, there's going to be a 50% chance of an eruption or a 10% chance or no percent chance?
Right, so I'm trying to think of what spaceweather.com does. I believe they use an algorithm that looks at classifications of sunspots. So it's a different classification scheme than this alpha, beta, gamma thing I'm talking about. They use, I think, Macintosh classification, which doesn't look at the magnetic fields of sunspots. It looks at just what the sunspots look like in white light and visible light. And these Air Force guys classify them in terms of their visible light configuration. And basically, the spaceweather.com looks at historically of each classification how many eruptions were produced by sunspots of that classification. So assuming that there's a certain rate of eruptions for each sunspot classification, when a new sunspot comes up, there's you can get a probability from that historical data. But that's quite separate from what I'm doing here, yeah.
So you're basically on an edge of a new systematic way of predictions.
Yes, yeah, exactly. Yeah, and that's sort of our science goal, is using complexity from Sunspotter to do these predictions, as opposed to using, you know, some of these Air Force things or other measures that have been used before. That's right. So this slide is just showing where we are right now in the project. We've just headed into phase 2. In phase 1, we had about 13,000 images. In this case, we have 200,000 images. At the moment, as you may have heard through the grapevine, that there's now 1 million Zooniverse volunteers. So it's actually feasible to do this scale of study, because we actually need millions of clicks or millions of classifications of sunspot complexity to get through the whole data set. So I just wanted to talk a little bit about the results, some of the results that we've gotten from the first data set. If you have any questions, let me know. It gets a little bit technical here, I think. So as I mentioned, we started with 13,000 sunspot group detections. And basically in about a month, I think 30 days, almost exactly, 1,600 volunteers had gone through the whole data set and done around 300,000 classifications. The images that we showed were 2 scales. So 2 different sunspots, no matter how, if one was really small and one was really big, they would see it like that. They wouldn't, we weren't just cutting a square around each one and then rescaling it. So people for space in the images. Once we got comparisons of a ton of different pairs of sunspot groups, we used something called the ELO ranking algorithm to go from a list of classifications to an actual list of sunspot groups ranked in order of complexity. So that's where we go from. So using that, we can actually get some science out of it. And the ELO has been used a bunch of times. For instance, it's used to rank chess masters. And the basic way it works is that it seeds every image or, you know, chess master or whatever you're trying to rank with some initial score, and then as 2 different things are compared, the difference in between their scores dictates what happens when one or the other loses. So with 2 sunspot groups, if one was initially classed as really complex and the other was classed as really simple, and then someone shows that the simple one was more complex than the one that the algorithm thought was complex, the score for the simple one would shoot up high. So basically, ELO is a way of getting the scores to converge on their quote-unquote true score more quickly than using some other algorithms. So as far as results are concerned, sort of the simplest result that we can talk about is which images do people class as the least complex and which do they class as the most complex. So in the top row is showing the least complex images. And as you can see, there's not really much stuff going on, or if there is, it's sort of just a bit of white or a bit of black or nothing there at all. Whereas on the bottom row, you can see really complex, really strong magnetic fields. So that gives us some faith that people at least classify things pretty overall correctly. Likewise, I've shown here the A, B, tells you whether it was alpha, beta, beta. So that means that's pretty simple stuff. on the bottom row, you can see that the Air Force class stuff is unknown, beta, gamma, delta, beta. So what I'm showing here is that sometimes their Air Force scores kind of break down. Sometimes they don't actually classify something as here as unknown, or sometimes there's two sunspot groups really close together and they class each one a beta, but in our case, we're calling it the same group, so it's actually a more complex thing. So I think there's a more useful way of in the end, we ended up with a more useful way of measuring complexity, at least as far as forecasting is concerned.
Well, there was a comment in the chat, or a question in the chat.
Yep.
About how do you decide which time periods and areas sunspots to analyze with volunteers, and what is the amount of time it takes to conduct these?
Right. So for our initial data set, we chose a data set that's actually been used in other studies so that we could compare our results with those studies. And that time period is most of solar cycle 23, which is a solar cycle that just happened. So that's from 2000 to 2005, 2006. So those 13 images would have been spaced over that amount of time. What is the amount of time? What do you mean by what is the amount of time it takes to conduct these?
So how long of the time frame does it take for people to count this up? I mean, what amount of time give volunteers?
Oh, well, it took a month to classify everything. Is that what you mean? Each classification, I think people do in like a few seconds.
So just a few seconds for classification is what you're saying, Paul, before it goes on to the
Okay. Yeah, sorry, I didn't quite understand. Yeah, people don't spend long on each one. That's for sure. So in this plot, I'm comparing alpha, beta, and gamma, delta classifications, which are those Air Force classifications, just so we can have sort of a benchmark to compare our stuff against. And the ELO score is basically the ranking of how complex each of our sunspot groups are. This is a histogram, so the y-axis is the number of sunspot groups for each ELO score bin. And so the red histogram is the Air Force says are the least complex sunspot groups, the alpha class ones. And you can see that distribution peaks at lower ELO scores than, say, the beta class sunspot groups, which peak a bit higher, and then sort of gammas and deltas peak even higher than that. What we really want to, so it shows that as those classifications that we would consider to be complex in that order from beta to gamma delta matches what we find in our complexity scores that our volunteers have given us. So that's a good sign. But what we really want to do is to go from ELO score to a number that's a bit more useful. So I came up with sort of a complexity score that just goes from 0 to 100 and sort of scales things a bit differently. So what we're really interested in these most complex, let's see here, this bump in the distribution over here is the most complex sunspot groups, and that's the stuff that we're really interested in because those are the ones that produce the eruptions. Andy, can you let me know how much time we have left?
It's 7 o'clock right now, so you have about 15, 20 minutes.
Okay, perfect. So in this plot, I've rescaled those distributions so that we take all the alphas and betas, all the least complex stuff, and smoosh it down to the bottom, the low complexity, and then we spread out the more complex stuff, so we get a better, what you might call dynamic range. And then this gray line is basically the distribution of sunspot groups that produce large eruptions. So you can see all the sunspot groups producing large eruptions are at the higher complexity higher complexity scale, which is what we expect. And that's sort of our main science result at this point, and sort of proves what we were hoping would be the case. So in this plot, we are taking complexity scale and we want to compare it to different physical properties, or properties that make more sense, like how much magnetic flux is there in a sunspot group or the area of a sunspot group. So in this plot, it's complexity versus magnetic flux. So this is just trying to show that, you know, if you're trying to explain this stuff in a classroom, you could compare complexity to different physical properties that you could actually talk about, or if you're talking about, you know, magnetism or so forth. This might be interesting for them. Let's see. There we go. So now I want to talk about a few of the outreach activities that we've run over the past year or two. One thing we did was a live, before we actually started the Sunspotter project, before it actually went live on the website, we did a test of Sunspotter classification rankings with a group of 15-year-olds in the Science Gallery, which is in Dublin, Ireland. So we had about 20 students, and we had about 15 different images of sunspot groups, and then we paired them up in like 100 different ways. And then we just showed the students the images one by one, and they picked which one they thought was more complex. So that gave us a really big data set of all these different students doing that. We also did the same thing with scientists in Finland, and it turned out the scientists had a much harder time with the project because they really wanted to know what we meant by complexity, and they got into all these details that the students were just kind of ready to go, and they just did it. So that was interesting to see. We found out with this way of doing it anyway, it's really labor intensive if you actually want to analyze all that data, because you get, you know, 20 different sheets of 100 different pieces of data each, and then you have to put those into a computer and analyze them. So we need to think of a better way of doing that that can sort of expedite the process. So we've just launched phase 2 of Sunspotter. We also did a launch in Dublin for the phase 1, which happened in February. And basically for both launches, we had a bunch of those students, and we gave a talk about explaining solar activity, another talk explaining citizen science and how people can get involved with science, even if they don't really know much about science. And lastly, a quick talk about the Sunspotter project. And then in both cases, we passed around iPads and had the students, you know, actually try out Sunspotter. And what I found, I did something like this with a group of very young students. I think they're about between 6 and 12. And the youngest students kind of didn't really get, I guess, the project. You know, looking at sunspots, it wasn't super engaging for them. So there are actually other Zooniverse projects that I was able to have them try, like one called Snapshot Serengeti, where they can go on and classify animals that are
Do not tell the teachers about that, Paul. They will never get off of there ever.
It is a really addicting
Adler, obsessed.
Yeah. Yeah. It turns out people really like to look at basically we sent a PhD student around to a bunch of different high schools and had him give a talk about the sun-earth connection, solar activity, and then ran a workshop where the students actually classified sunspots in terms of this Hale classification I was talking about. So they told us whether it was alpha, beta, beta, gamma, and then we had an explanation of each classification, so they could do that. And then they were able to actually recreate that plot that I showed in the beginning. This one here, which you know, is a professional scientist plot, and they were able to make their own plot, this one here, and compare to it and show that, you know, they could actually do something comparable to professional research and you know, intercompare the results. And there is a full description of this project online down here, so you can check that out later if you want. also, I wanted to talk about, we do have some educational resources available on our Sunspotter website. We have links to some videos, NASA videos, and videos of our guys talking about the project. We have some PowerPoint slides from some of these talks that we gave to students and the public. And we also have that activity description that I just talked about in the last slide. So you can check out this stuff on ZooTeach. Another thing we have on the Sunspotter website is Talk, and I think all Zooniverse projects have a version of this. So after someone classifies some sunspots, they can then go on and discuss the sunspot images, or just present, just give a random discussion or something they're interested in, or some question they have about the data, all kinds of stuff like that. And myself and some of the other scientists actually go on to talk and interact with people. So it might be fun for students to go on and actually ask some questions to scientists running this project, if they're, if it's being used in their classroom.
And I think almost all of if you use other Zooniverse projects, all of them do have that feature in that talk. So if some of you are familiar with Galaxy Zoo and Hanny's Vertorp, that's how that was identified, was through this talk feature. So it's really in all of, I know for Sunspotters for sure, the talk part of it is actually archived. So your students can go back, if they have questions, they can go back and see some of the other conversations with scientists as well.
Yeah, that's right. So then I just wanted to talk about, I think it's my last slide, some future resources that we'd like to develop. So I'm not sure, it's not clear to me whether the resources I've showed so far would be useful in the classroom. So I wanted to get some feedback from you guys on that. But one thing we are interested in adapting to Sunspotter is something called the Data Navigator, which would allow people to go on, have a classroom, go onto Sunspotter, and make a group on Navigator. So then they'd be able to classify a subset of the sunspot groups as a class altogether, and then they could see the ranking that they came up with as a group. Afterward, they could then make graphs or plots of the different physical properties of the sunspot groups that they classified. So they could plot the total area of the sunspot groups versus the total magnetic flux, or against complexity, and then determine whether different populations produce flares or not, so they can see what sorts of sunspot group properties lead to eruptions or flaring.
This is Andy. Now explain. Will you talk a little bit about the Navigator piece, because this is a selected set of data, right? That is meant to.
Yeah.
Can you talk about that a little bit? Because many of the other, I've worked with Planet Hunters, and we do the same thing with Planet Hunters. Is so that you have an opportunity to use the actual data that is selected, and you don't have the chance piece. Can you talk about that a little bit?
Yeah. So I mean, as an example, this works for Galaxy Zoo. What you could do is take 100 different galaxies as a subset, and then in your classroom you could say, okay, you could pass out iPads and have everyone go onto this Navigator web page, and then pick your class as your group, and then for those 100 galaxies, you could all as a group classify those galaxies, as spiral, elliptical, or whatever the other Galaxy Zoo classifications are. So that data set would be yours, sort of, for your classroom, and no other volunteers around the world or anybody else would be involved in that. It would just be your class. So on the back end, that after you've classified everything, that would sort of give you, a classified set of data that you could then analyze as a classroom. And by analyze, I mean you could make, look at the total set of data altogether, all the images. You could make histograms and say, okay, how many different galaxies had this classification, how many had this classification, or also you could make scatter graphs where you could plot the different properties against each other, like I was talking about. I think in the case of Galaxy Zoo, you could plot the color of the galaxy versus the size of the galaxy, or the how old the galaxy is. Look at galaxy evolution that way. So likewise, you could do similar things with Sunspotter. So if anyone has any questions or You want me to explain anything else more in depth? Let me know.
No, I just so the teachers understood that they had their own data set and could actually be using real data. So that is theirs that they could then manipulate in different ways. Not manipulate, but categorize and analyze in different ways. That was all.
Yeah. So that's pretty much all I have. And basically, I just wanted to get feedback from all of you. If you think a navigator for Sunspotters would be something you'd be interested in using in your classrooms, or how you might, if you have any ideas about how you might tie Sunspotter to your curriculums, or some of the other examples I showed, whether you could use those in your classrooms.
Diane, you put that your astronomy students would be doing this, certainly be doing this next year. How do you see yourself using that with your astronomy students? Can you hear me, Diane, or? Oh. Sunspot. So how specifically do you think that you would use the Sunspotters one?
Well, as we go through the different units, anytime I can put the kids in front of a computer and say, go to this website and do this, it just gives so much more meaning and so much more power to everything that it just, it's authentic. It's data they can work with, and that's the power of this.
So what do you think you would use it in conjunction? What do you think that you would, how would you pair this up? Is it just something you would randomly say here? You know, like Laura pointed out that she uses Serengeti as a reward, which I'm serious, don't go there. You guys will just have a conversation on Facebook. But you know, as a reward, because but do you see it as, how would you use it contextually in your classroom? I know I'm putting you on the spot, Diane.
Well, no, I actually have a lab where they are ratty old black and white photographs that could have been taken by Edwin Hubble himself, and they are all the different things, and it's like, how would you classify these? And so they, you know, we spend a little bit of time, and some of them try to do an evolutionary sequence, and some of them just do spirals and ellipticals and the irregulars. And so, I mean, that's been a lab forever. But for me to be able to put them in front of a screen and have them work with real images of galaxies that are out there, just, that's breathtaking.
Okay. So would you, I guess, would some of you be then interested in, you know, having some discussions later on and talking about specifically how we would implement some of this and make an interface like Navigator?
Yeah.
Well, great. My 2 cents on this one, I do a unit on space weather, and with that, we normally end up and said, okay, the sun just had an eruption, we got a coronal mass ejection, and here it comes. I have never been, okay, where does that come from? How do you know how can we predict, using data, can we predict that's going to happen? And so I can see it as a lead in to my unit on space weather. Because then they can start looking at the complexity of these various sunspots and say, okay, if you see one like this, that might be worth watching. See one like that? Nah, don't worry about it. It would give them authentic data to look and be able to predict.
And Paul, this is Ricky from Space Science Lab. Could you interface it with the J Helio viewer so they could make predictions and then use the J Helio viewer to see if that was actually what happened on the day that they predicted it?
On the day they predicted it, they could use some of the NOAA data, because J Helio viewer I don't think is quite up to date enough. So like if you're looking for data from today, I could send you a movie. There's a movie that's updated every day, and it shows you what flares have happened and you basically just see flares going off like up to the last, I think, half hour, up to the last hour of time. So I'll send that around actually.
Yeah. Well,
that would be great if you could predict it, but I don't think it's really that necessary, as long as the students can see a cause and effect. That, okay, here's a sunspot. This is how it developed. We considered it complex, and then we have proof that it erupted. Or we decided this sunspot was an alpha and it went away. Nothing happened. You know, even if it happened 3 years in the past, it gives us the ability to look, to predict, and get results.
Oh, okay. Well, actually, for that, I would probably use solarmonitor.org because you can click back in time, and you can click by solar rotation or by day. And then you can see what sunspots were on the sun, and then below, at the bottom of the page, it shows which of those sunspot groups produce flares and how big those flares were.
Yeah. And I think being able to visualize the data that they're collecting is really powerful for students.
Okay.
I would think,
and somebody else. Sorry, go ahead.
I was just going to say, to me, this takes the sunspots out of the abstract. It seems to me, you know, when you talk about sunspot, or when I shouldn't, you know, and I haven't worked with heliophysics with students for a number of years, but you know, it takes it out of a quality of the sun into something that is an entity of its own and has its own uniqueness about it. You know, it's not just a freckle on the sun, I guess is how I had one student talk about it, but this now you can look and see how this is not only a quality of the sun, but also its own dynamic piece that has cause and effect, I guess. I think that's really interesting about this project.
Okay. So it sounds like most people are interested in, or it'd be really good if we could know which ones actually produce flares. And actually, back to this talk.sunspotter.org, one of the metadata pieces that we have after you classify a sunspot group is it tells you whether it produced a major or a small flare in the next 12 or 24 hours. So that might be useful. It says
when you're working with kids.
Yeah.
When you're working with kids, you almost always have to end up with an end product. In other words, if they're working on something, they don't see an end product, they'll lose interest real quick. But if they see, hey, this is what happened, it could happen 2 months ago, and they'll still be excited that they got a chance to see it happen and to be able to make a prediction. But to not have an end product, I think it would get, I don't think it would last long.
Okay.
What are the curricula tie-ins that you all see? Again, you know, it's been so long since I've, you know, my work with in a classroom with heliophysics has been a few years ago. But what do you see as it fitting into what curricula you already use in your classroom? How could this enhance it or be an add-on for you?
Well, I just went on Zooniverse, and I really like it. I'm actually this week writing a curriculum with the 8th grade math teacher, and we're focusing on some of the Texas TEKS, and I know also the National Science Standard talks about the different components of the universe. So this is a really great website that I can incorporate into writing my curriculum tomorrow. So this is great timing, and anytime that a student gets on the computer and uses technology, administrators like that, and students love getting on the computer, and this is a great website, I think, that I can actually incorporate into my new lesson. So thank you for sharing that.
Great. Somebody was saying, I do need a review of the HelioViewer, Sally Jean. Do you want me to explain what HelioViewer is, or?
Claire actually did, as part of our virtual retreat last year, she did a breakout session on HelioViewer and HelioJViewer. And so I think that's what Sally was referring to, is going back and using, looking at the platforms again, which we all do need. So, because we were all fascinated with it as well. But any other curricular tie-ins that you guys see, or what you already teach in your class, how this might tie in with what you already do, as far as helioscience and sunspots?
Well, it's not, for me, it's not so much tying it in with the heliosciences, but bringing it in, because where we are with middle school in Texas, our TEKs aren't specific to heliosciences. So some of them are, but not as much as we would like. But what we would do, or what I would do, is certainly pull this, and as I put in the group chat earlier, pull this and use it during our Nature of Science unit, which is a 3-week unit that we always have at the very beginning of the school year. And so what you're doing is you're learning during that 3 weeks, the children are learning how to think like a scientist, and how to question like a scientist, and how to use the tools that a scientist uses. And that incorporates basically 4 very specific standards for the state of Texas. And this would be fantastic for that, something new and different. And Molly, when you're writing curriculum tomorrow, think about putting it in there as well, because it's a really good spot for all of this as well. You know, and again, everything is just sort of clumped differently, but you can certainly justify using this, because we are asked to have students use real-time data. And this is perfect for that. So thank you again.
Well, and not to forget that these projects are, you know, especially so when your students use Sunspotters, they're helping Paul. You now have a face to put that in there, that they are doing work for him, so that they are analyzing data for him, so that he can actually use that very, very quickly. Stuart, so anybody who wants to make a field trip to the Adler, the Zooniverse is, part of it is housed at the Adler. And Stuart Lynn, one of the project leaders, has a lovely thing that I'll share at another time about how this analysis really does allow scientists like Paul to do their work very, very quickly and see results very, very quickly. And so, you know, I think that's an important piece, is that you now have a face to say you are helping this man do his research and be able to do really amazing things by doing that. You're all invited to the Adler all the time, so please know. I have a 1-bedroom apartment, but I have lots of floor space. So good. Any last questions for we? I do want to be respectful of our time at 7:24, so we have about 6 minutes left. But any last questions for Paul? Or yes, that they are helping with current research. It is so important that the students understand that this is real. It's not a game. It's not a video game. It's real. And Paul, I'm sure, is grateful that they're helping. But any last questions for him?
Great, thanks a lot.
So Paul, you're using Sun Cycle 23. What about Sun Cycle 24?
Yeah, I should have mentioned. So for phase 3 of Sunspotters, we're going to transition from MDI to HMI data. So the resolution will be a lot better, as I mentioned before. And the data will take us up into the current state of the sun. So we have about, it's 2014 now, so about 3-4 years of data from HMI for people to classify. And once they get through all that, then they're classifying real-time data. And presumably we'll be able to create a flare forecasting algorithm based on sunspot complexity. So it's conceivable that people could actually be doing complexity classifications that are fed into this flare forecasting algorithm, and we could actually, make, a percentage of, is this particular sunspot group on the sun going to flare, 15%, 20%, whatever it is, and that'll be based on people's classifications in real time.
Well, thank you so much, Paul. I'm going to email you tomorrow, and we can talk about how to get you on the Wigio and post this amazing work that you've done and your slideshow, if you'd be willing to share it with us. I know that teachers do go back, even though we record things, these teachers do go back and look at these slideshows and figure out how to use them in your, Nancy, it is a public thing, so anybody can use it. Oh, wonderful, Vic. I'm glad you can use it in your class. I will post some things on the Wigio tomorrow about Zooniverse itself. I am a little biased about it because it is at my institution, and I work with these incredible people that help make this thing real. So anyhow, but Paul, we'll talk about how to get your stuff on there, and I know that teachers will have questions for you. So as they digest all this amazingness that you've just shared with us. So thank you for taking the time, and we hope that you'll kind of lurk in our community a little bit so that we can continue to ask you questions and involve you in this work.
Yeah, absolutely. Thanks for having me.